So we'll now introduce Taylor polynomials. What are Taylor polynomials? Well, these are polynomials that have some tangency in some point to the graph of a function f. So we try to find, in this video, I try to find a formulation of these Taylor polynomials. So the problem is, suppose I have a function defined in an open interval and a is contained in this open interval. Why do we need an open interval? Well, suppose that we want to differentiate the function in a, and not only that, we want to determine the nth the first order derivatives up to the nth order derivative of a function in a. Then suppose we know these values. Then the question is, can we find a polynomial? Can we find a polynomial t? Well, the t stands for Taylor, but that's just a name, of degree n in that point a, so that the graphs of f and t are tangent to order n in that value a. Can we find such a polynomial? Well, in the coming I will show that this is pretty much straightforward and that we can calculate such a polynomial. So we're just gonna do this brute force, right? So let's say we have the following description of a polynomial of degree n. It's c0, it's a constant, plus c1 times x minus a plus etc. etc. We can express any polynomial like so, plus cn times x minus a to the power n. This is clearly an nth degree polynomial, and we want to look if we can find constants c0, c1, c2, and cn such that this polynomial is tangent to order n to the graph of f in a. Well, we'll do a brute force, so we'll just take the conditions that need to be satisfied and see that there are constants to make this going, right? So at 0 we need that the t of a should be the f of a. The f of a should be the t of a, right? But if we plug in a in the polynomial, then the only thing that remains is c0, right? So we get c0 plus 0 plus 0, etc. So that would mean that c0 would need to be chosen as fa, right? So there's no other possibility than that c0 should be the f of a. Now the second condition. The second condition states that the derivative in a should be equal to the derivative of t in a, right? So let's say that first we take the derivative of t and then plug in the value x equal a, right? So what is the derivative of t? Well, we're gonna take the derivative of c0, which is 0. We're gonna take the derivative of the second part, which is a linear part, so we get c1, and c2 2c2 times x minus a, etc. And here the n goes forward. We get n times cn times x minus a to the power n minus 1. So what we do is we get this polynomial, and then we plug in the value x equals a, right? So if we do that, and we see that starting with c2, the term x minus a cancels, right? And completely to the right, right? So we get here that c1 is the only thing remaining, right? So if we want to choose a polynomial that has a tangency of order n in x is a, then c1 should be chosen equal to f prime of a. Okay, so this machinery does work, so far. So we is working so far. So now we look at the second condition. The second condition says that the second order derivative in a of f should be equal to the second order derivative of t in a. So what does it mean? Again, we do use the same procedure, right? So we first calculate the second order derivative of t and then plug in x equals a. So that means that now we get 2c2 3 times 2 c3 times x minus a plus n times m minus 1 cn times x minus a to the power x minus 2, right? Since the second order derivative is the derivative of the first order derivative, right? So we see that after 2c2, all possible terms are canceling, right? So these are all zero when we plug in x equals a. So we get as a result by substituting x equals a, we get 2c2. This means that c2 should be equal to the second order derivative of f in a divided by 2. Yeah, and this will be just continue. So we have condition 3. Condition 3 says that the third order derivative should be equal. So again, we calculate the third order derivative of t, which now equals 3 factorial c3 plus x minus a to the rest, right? So again, we have a rest term, right? So if we just, regardless the constants that we have here, if we plug in x equals a, then the rest will just cancel out since I have an one common term which equals x minus a. So what I get is 3 times 2 times 1 times a c3, which is 3 factorial c3. So c3 should be equal to the third order derivative of f in a divided by 3 factorial. Well, the procedure is just the same. We keep adding terms, the powers, they getting down, right? So if we take derivatives, then here, for instance, we get n minus 2 times n minus 1, then times n minus 3 times n minus 4, etc., etc. So if we look at the kth derivative of t, and so that we have the kth order derivative of t, and we plug in x equals a, then we get k factorial times ck. Yeah, from which we deduce that ck should be chosen as the kth order derivative of f in a divided by k factorial. And this should hold for k is 0 until n. So basically, there's only one polynomial that is tangent up to order n in x equals a. So we get the following conclusion, right? So if we want to have a polynomial that is tangent up to degree n to the graph of f in a, then we write this polynomial as c0 plus c1 times x minus a, etc., etc., plus cn times x minus a to the power n. Then c0 is fa, c1 is f prime a, c2 is f double prime divided by 2 factorial, which is equal to 2, etc., etc. We may continue until the final one, the nth order derivative in a divided by n factorial times x minus a to the power n, right? So, and this function is now called the nth order Taylor polynomial for f in a. Yeah, so that's the definition. And you may check yourself that this polynomial indeed is tangent to the graph. The graphs of t and f are indeed tangent to order n at x equals a. So sometimes if we feel the need to write down exactly at what point we make and for what function we make the Taylor approximation or the Taylor polynomial, then we use a superscript f and a.